Before we dive into the mystery of interstellar comet 3I Atlas, welcome to Heraverse, where space is not just a backdrop, it is the main story. If you love deep science explained in a calm, cinematic way, hit subscribe and turn on the notification bell so you never miss a journey beyond our solar system. If this video helps you understand 3I Atlas a little better, please like the video so more curious minds can find it. And if you know someone who is obsessed with cosmic mysteries, share this episode of Heraverse with them. Let's explore the universe together. The discovery does not begin with a flash in the sky, but with quiet software stepping through wide-angle images from an automated survey. On a cold, digital night in early July of the year 2025, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to watch for hazardous near-Earth objects, records a faint, moving point among the background stars. The system is built to notice motion, to compare one image with the next and mark anything that drifts or jumps. And on this night, it flags a candidate that seems unremarkable at first. It is just one more speck sliding against the fixed field. Yet when astronomers, led by Daryl Seligman, examine the track more closely and begin to fit an orbit, the pattern refuses to behave like an ordinary comet or asteroid. The object carries a provisional label tied to the survey that found it, and soon it receives a name that hints at its nature: 3I Atlas, the third known interstellar object and the first found by this particular sky patrol. From the beginning, its path is wrong for anything born in the solar system. Where most comets creep along long stretched ellipses, bound to the sun in repeated returns, the orbit of 3I Atlas is a steep hyperbola. The calculations, refined with each new observation, show that if one follows the curve backward in time, it never closes. Run the equations forward, and the same open curve races back into interstellar space. The sun does not hold this visitor. It merely bends the track of something that already moves too fast to be caught. Follow-up observations begin almost immediately. Larger instruments, like the Canada-France-Hawaii telescope and the Very Large Telescope, turn toward the faint point marked in the survey images, measuring its position night after night. Astrometry, the careful recording of exact coordinates against distant background stars, sharpens the orbit and reveals the true speed. The numbers that emerge are striking. 3I Atlas approaches and departs with a hyperbolic excess velocity of roughly 58 kilometers per second, far above the escape velocity of the sun at the distances involved. In simple terms, even without the sun's gravity, it would still be racing through the galaxy at tens of kilometers each second, a remnant of some distant planetary system flung free long ago. Where the first known interstellar visitor, often remembered for its elongated shape and puzzling behavior, drifted through at about half this speed. And the second, a bright and active comet, traveled somewhat faster. This new object doubles those earlier values. The solar system has never recorded such a rapid, natural body on a clear, outbound trajectory. Velocity alone is enough to mark it as foreign. Yet other elements of its path also draw attention. The inclination of its orbit, the tilt with respect to the plane in which the major planets move, measures about 175 degrees. That is only a few degrees away from the ecliptic plane itself. In effect, the comet sweeps in on a near mirror image of the planetary disk, almost aligned, yet slightly flipped, approaching and departing in a way that feels eerily well placed amid the architecture of the solar system. Size estimates follow from the measured brightness. When sunlight reflects from a dark, distant body, its apparent magnitude gives a rough sense of how large it might be, provided one makes reasonable assumptions about how much light the surface reflects. Early models suggest that 3I Atlas is far larger than the earlier interstellar visitors. Where the first was likely only a few hundred meters along its longest axis, and the second just under a kilometer across, this new arrival appears to span several kilometers, perhaps between 5 and 10, depending on its reflectivity. The exact figure is uncertain, yet even the most conservative estimates place it among the more substantial comets ever seen on a hyperbolic path. The light curve, the way its brightness changes as it rotates and as its orientation shifts, tells a subtler story. Unlike the dramatic fluctuations seen in the elongated first visitor, this comet maintains a relatively steady brightness over time. The simplest interpretation is that its shape is closer to a sphere or a compact, irregular body, rather than an extreme needle or flattened shard. A more rounded object shows less variation as it spins. Combined with its inferred size and its high speed, the picture begins to form of a massive, dark, almost featureless interstellar nucleus passing through the solar system on a single, brief visit. Color information adds another dimension. As telescopes with sensitive detectors split its light into basic components, they find the object is noticeably red, more akin to the darkest outer belt asteroids than to the icy bodies that haunt the far Kuiper belt. A redder tone often hints at complex organic-rich material on the surface, processed by eons of radiation. In the case of 3I Atlas, the color index appears consistent with so-called D-type asteroids, objects that, in the solar system, typically orbit beyond the main asteroid belt, but inside the realm of the most distant frozen worlds. It is a curious match. A body that clearly did not form here, nonetheless carries a spectral fingerprint reminiscent of a specific class of local objects, as though separate planetary systems distill similar materials under similar conditions. Or perhaps the resemblance points to deeper differences, subtle shifts in composition and texture that will only become clear as more data accumulate. At this early stage, astronomers can only note that the incoming body seems darker and redder than expected, a compact, fast-moving ember, rather than a bright, icy shard. As the story of the discovery, observing proposals are revised, telescope schedules are shuffled, and plans are made to track it as long and as precisely as possible. For those who study small bodies, it represents a rare experiment that the galaxy has dropped directly into the inner system. Instead of sending a spacecraft across light years to sample the debris of other stars, here an ancient fragment has found its own way into reach, carrying in its mass the history of a planetary environment that no probe has ever visited. Its orbit, size, color, and speed form the first sketch of its identity, but already the sketch feels incomplete. The orbital alignment seems almost too well tuned to our planetary plane. The inferred age implied by its passage through interstellar space suggests that it has spent time in environments very different from the present-day solar system, and its subdued light curve implies a shape that hides its internal structure behind a nearly uniform exterior. Each new measurement clarifies one aspect while deepening others. This is no routine comet discovered on a sleepy night at a survey telescope. It is an object from another sun, arriving fast, large, and strangely familiar, announcing itself through numbers that both inform and unsettle, and inviting the first of many questions about what, exactly, drifts inside that dark red shell. The first firm orbit for 3I Atlas does not arrive with a dramatic announcement, but with careful iterations of fitting and refitting as new positions come in from telescopes around the world. Each night, observatories feed fresh coordinates into numerical models that solve for the path of a small body under the gravity of the Sun and the planets. With every added point, the uncertainties shrink, and the curve that describes the comet's motion grows sharper. What emerges is a hyperbola that cuts through the inner reaches of the solar system in a single, sweeping turn, a path defined by a high incoming speed and a pronounced but brief bend around the Sun. The parameters that describe this curve are ordinary tools to dynamicists, yet in this case, they take on an unusual character. The eccentricity, a measure of how stretched an orbit is, lies well above the value that separates bound ellipses from open hyperbolas, underscoring again that this object arrives from interstellar space and will not be captured. The perihelion distance, the closest approach to the Sun, falls near the orbit of Earth and Venus, threading between the inner planets in a way that feels more like a probing pass than a random plunge. The inclination, the tilt of the orbit relative to the plane of the planets, hovers close to 175 degrees. This means the comet travels on a path that is almost coplanar with the familiar disk of the solar system, but moves in a slightly reversed sense, skimming just a few degrees away from the ecliptic. Instead of diving steeply above or below the planetary plane, as many long-period comets do, 3I Atlas comes in almost along the same flat sheet that contains the orbits of Earth, Mars, Venus, and Jupiter, as though it has chosen a highway that was already drawn long before it approached. Astronomers are cautious with such language. They know that gravity does not plan, and that a hyperbolic orbit can in principle arrive from any direction. Yet the near alignment invites questions. Some suggest that detection bias plays a role. Surveys are often most sensitive near the ecliptic, where most known asteroids and comets dwell. So perhaps interstellar visitors on other trajectories have simply gone unnoticed. Others note that the Sun's gravity acts like a lens, slightly focusing the paths of passing objects. Over billions of years, the configuration of the planetary system and the gravitational field of the disk of the galaxy may make some approach angles marginally more likely than others. In this view, the neat passage of 3I Atlas close to the planetary plane might be a statistical echo of subtle selection effects, rather than a deliberate alignment. Still, the raw orbital elements carry a certain tension between chance and pattern that helps drive the sense of mystery surrounding this object. The same solution that defines the shape and tilt of the orbit also predicts where and when the comet will pass near major bodies. As the trajectory is integrated forward, the path swings past Mars at a moderate distance, then dives inward to a perihelion somewhat farther from the Sun than the orbit of Mercury, but still well inside the Earth's orbit, before climbing back out toward the realm of Jupiter. Along the way, the orbit carries 3I Atlas to within a fraction of an astronomical unit of several planets. It glides inside the orbit of Mars in early October of its passage, close enough that spacecraft orbiting the red planet can try to capture images of the fuzzy nucleus and its emerging coma against the dark sky. Later in the month, it comes nearest to the Sun, at a distance that balances solar heating and survival, warm enough to drive vigorous activity, but not so close as to tear the nucleus apart. In early November, the geometry brings it into a position where, from the standpoint of Venus, the comet passes at a distance a little smaller than the gap between Earth and the Sun. From Earth's perspective, the encounter in December is more distant, but still close enough to permit detailed remote sensing. Finally, by March of the following year, the object's outbound leg carries it to a point where its path in three-dimensional space crosses relatively near Jupiter's orbit, within a distance comparable to a bit more than 1/3 of the separation between Earth and the Sun. None of these passages qualify as close shaves by the standards of planetary defense. The comet does not threaten to strike any planet, and its minimum distances remain comfortably large compared with the gravitational spheres of influence of the worlds it passes. Yet, in astronomical terms, these encounters are near enough to be scientifically rich. Each flyby provides a new vantage point, a chance for orbiting spacecraft and ground-based observatories to sample the coma and tail from different angles and different wavelengths. The orbital solution thus becomes not only a description of motion, but a map for opportunity, marking windows when instruments scattered across the solar system can catch this fast traveler in their fields of view. When astronomers plot the orbit in a rotating frame that follows the Earth around the Sun, another pattern becomes visible. The path of 3I Atlas appears as a sweeping curve that slices inward from the outer solar system, loops around the Sun in a sharp turn, and then flings itself outward again, crossing the tracks of the planets at several points. On such diagrams, the near coplanar nature of the orbit stands out. While many long-period comets slice through the planetary orbits at steep angles, this interstellar visitor almost shares their flatness, tracing a thin ribbon that lies close to the same geometric plane. The nodes, the points where the comet's orbit crosses the ecliptic, fall not far from the orbits of Mars and Jupiter, reinforcing the sense that it weaves through familiar celestial lanes. In classrooms and public talks, scientists sometimes overlay the orbits of the 3 known interstellar objects discovered so far. The first came in on a steeply inclined track, the second on a more modest tilt, and now the third glides in almost along the planetary disk. Seen together, they hint at a diversity of approach directions, but also at a gradual filling in of parameter space. With only a few examples, no one can claim a robust pattern, yet the latest arrivals near alignment suggest that future surveys may find more such interstellar comets hidden among the forest of orbits that crisscross the ecliptic. In numerical simulations, researchers explore how 3I Atlas would have moved through the solar system if the planets had been in slightly different positions at the time of its passage. Small shifts in the phase of Jupiter or Mars alter the distances of closest approach, but do not fundamentally change the hyperbolic character of the trajectory. The comet enters, swings around the Sun, and leaves regardless. This robustness underscores that the passage is not finely tuned in a way that would require special explanation. Yet the simulations also reveal that, had it arrived a little earlier or later, its distances to certain planets could have been slightly smaller or larger, altering observational opportunities. In that sense, the actual configuration experienced by humanity is a particular slice through a broad range of possibilities. It is neither uniquely privileged nor entirely trivial. For the observers living through it, the actual dates and distances matter because they determine which instruments can turn toward the comet and when. From the standpoint of the galaxy, they are simply one more set of coordinates in an endless sequence of encounters between wandering debris and planetary systems. Still, even this sober perspective does not quite erase the feeling that this interstellar fragment is threading a narrow corridor through the inner solar system. The numbers that define its orbit are precise and impersonal. Yet when translated into images of moving paths and planetary alignments, they sketch a story of a stranger who passes close enough to be studied, but not close enough to disturb. It seems to know the layout of the solar system without having seen it before. The coincidence is likely just that, a coincidence shaped by observational biases and gravitational dynamics. But for the scientists tracing its trajectory, night after night, it lends a quiet, persistent strangeness to an already remarkable visitor. From the first nights after its identification, 3I Atlas is more than just a moving coordinate on a star chart. As larger telescopes lock onto the faint smudge of light and track it across the sky, astronomers begin to extract subtler information encoded in the way that light varies. Every small body in space turns, and as it turns, different faces catch sunlight and reflect it back toward distant observers. The resulting changes in brightness, plotted over time, form what is called a light curve. For an object tumbling end over end with a long stretched shape, the light curve often shows dramatic swings as the long side and short side alternately reflect more or less sunlight. The first interstellar visitor displayed exactly this kind of behavior, with sharp rises and falls that hinted at an extreme aspect ratio, more like a shard than a sphere. The second known interstellar comet, more conventional in appearance, still showed modest periodic changes as jets of outgassing lifted dust from its surface and exposed brighter or darker regions. When astronomers build a light curve for 3I Atlas, they expect at least some unevenness. Instead, they find a pattern that is almost gentle. The brightness does change with time, and careful analysis does reveal a rotation period, but the amplitude of that change is relatively small. The object does not flash between bright and dim states. Its light only wavers. High signal data from large ground-based telescopes show that 3I Atlas seems to complete a rotation in roughly 17 hours, a moderate spin rate for a body of its size. This period is derived from repeating ripples in the light curve, small variations that line up when observations from many nights are folded over the same timescale. If the nucleus were sharply elongated, the difference between its brightest and faintest phases would be pronounced. Instead, the modest amplitude suggests that the shape is closer to a sphere, or at least a more compact irregular form where no single axis dominates. A roughly spheroidal or rubble pile body with a mix of slopes and depressions would produce just this kind of subdued variability. The inferred rotation period is neither extremely fast nor unusually slow. Many solar system comets and asteroids of similar size rotate on timescales between several hours and a day. In that respect, 3I Atlas appears unremarkable, another world shaped by the same basic principles of angular momentum and collisional history that govern local small bodies. Yet the very ordinariness of its spin contrasts with its extraordinary origin and speed, reinforcing the idea that the physics of small objects may be universal, while the environments that produce their compositions and trajectories can differ dramatically. Color measurements add a more distinctive layer. By observing the comet through filters that isolate different parts of the spectrum, astronomers can estimate how much light it reflects in the blue, green, and red bands. These relative intensities can be combined into color indices, which serve as fingerprints of surface composition and texture. Observations from large aperture telescopes, including a 10-meter class instrument in the Canary Islands and the Gemini South telescope, show that 3I Atlas has a pronounced reddish hue. Its reflected light is significantly redder than that of the second interstellar comet, and redder still than the already unusual first visitor. When compared with catalogs of solar system bodies, the color matches most closely with a class known as D-type asteroids. These objects, found mostly beyond the main asteroid belt, are dark with low reflectivity and display steeply reddened spectra that suggest surfaces rich in complex organic compounds and primitive carbonaceous material. D-type asteroids are thought to be among the most ancient and least processed remnants of the early solar nebula. To see an interstellar comet whose colors resemble this group leads to an intriguing convergence. It hints that the disk of gas and dust around another star might have gone through similar phases of chemistry and aggregation, producing outer planetesimals whose surfaces evolved under long exposure to cosmic rays and ultraviolet radiation. On the other hand, the precise match is not perfect. Spectral slopes and subtle features in the reflected light indicate that while 3I Atlas resembles D-type bodies, it is not identical. There may be differences in the exact mixture of organics and ices, differences that will only become clearer as more detailed spectra are obtained. Surface brightness provides another clue. The albedo, or overall reflectivity, can be estimated by combining measured brightness with size estimates from independent methods. Analyses suggest that 3I Atlas is very dark, reflecting only a small fraction of the sunlight that falls upon it. This is again consistent with a surface coated in complex carbon-rich compounds and possibly fine dust that has been processed by radiation over immense spans of time. In the solar system, meteorites like the Tagish Lakefall, which landed in Canada near the turn of the century, show similar low reflectivities and primitive compositions. Some researchers draw cautious parallels, suggesting that if fragments of 3I Atlas could be held in the hand, they might resemble certain rare carbonaceous meteorites known on Earth, mixed with unfamiliar phases that record conditions in a distant protoplanetary disk. Yet for now, those resemblances remain speculative. All that can be measured directly from afar are the integrated colors and the way that light waxes and wanes over hours and days. Even within these limited data, small anomalies appear. Detailed modeling of the light curve indicates that the rotation is likely simple and near principal axis, meaning that the object spins in a relatively stable fashion. There is no strong evidence for tumbling or complex precession. For a body that has spent untold millions or billions of years crossing interstellar space, one might expect impacts, tidal encounters, or outgassing events to have imparted more chaotic motion. The stability suggests that whatever reshaping events have occurred in its past either damped out over time or never pushed the nucleus into a wildly irregular rotation. In another sense, the stability could mean that the comet has not experienced many strong torques from outgassing, which would spin it up or slow it down. This idea fits with other observations that 3I Atlas, while active, does not display the violently asymmetric jets seen in some solar system comets near perihelion. Instead, its activity may be more evenly distributed across its surface, or confined to regions that do not produce strong net torques. Taken together, the nearly spherical implied shape, the moderate and stable rotation period, and the subdued variability paint a picture of a quietly turning object, an ancient stone and ice fragment rotating in darkness long before it ever approached the sun. In this picture, light from distant stars and galaxies glances off its rough surface, absorbed and re-radiated countless times as it wanders between stellar systems. Only now, as it enters the inner solar system, does that surface brighten enough for detailed study. And even then, it reveals itself only grudgingly, offering simple curves and gentle colors instead of dramatic flashes. The comparison with the earlier interstellar visitors sharpens the mystery rather than resolving it. The first was a bizarre, elongated body with a highly variable light curve and a puzzling, non-gravitational acceleration. The second was a more conventional comet with a visible tail and clear signs of volatile-driven activity. Now the third presents yet another face, a large, dark, roughly rounded nucleus with modest brightness variations and colors reminiscent of one of the most primitive classes of solar system asteroids. If all three come from the debris fields of other planetary systems, why do they differ so strongly in shape and behavior, yet share certain broad traits like low albedo and ancient surface processing? One possibility is that they sample different zones within their home systems. The first might have been carved from the inner regions of a disk, the second from a more traditional comet reservoir, and 3-1 Atlas from a transitional zone near a frost line where certain ices condense while others remain gaseous. Another possibility is that their current forms reflect long stories of collisions, close stellar flybys, and thermal histories in interstellar space, rather than just their birthplaces. In that view, the rounded, quietly spinning shape of 3-1 Atlas may be the result of repeated micro-impacts and slow reshaping under extremely weak forces acting over astronomical timescales. The light that telescopes capture now is the final state of many such processes, layered upon one another until only subtle hints remain. As observatories continue to gather photometric and spectroscopic data, models of the nucleus become more refined, but still incomplete. No direct image can resolve its surface, and so every inference about shape and spin must pass through the filter of integrated light. Nonetheless, within those constraints, 3I Atlas stands out as a stable, dark, reddish body, larger and more massive than its known predecessors, turning at a measured pace and giving away just enough of its nature to invite speculation. In this combination of well-behaved rotation and exotic composition, the comet suggests that other planetary systems may produce familiar structures under unfamiliar conditions, and that the shapes of interstellar debris can be ordinary, even when their histories are not. The mystery here is not a flashy anomaly, but a quiet tension between the expected and the observed, between the simple curves of a light plot and the vast uncharted past that those curves imply. Long before the official announcement of 3I Atlas, long before its path and speed are known, the comet's faint image has already crossed the sensors of powerful survey instruments that were not looking for it. In the weeks after the initial discovery, When the hyperbolic orbit and interstellar origin become clear, astronomers turn their attention backward in time. They ask where the comet was in earlier months and whether any wide-field telescopes happen to record that region of sky. Modern astronomy keeps enormous archives, vast collections of images and light curves stored from instruments that scan the sky with regular cadence. Within these databases, unnoticed interstellar visitors may already be hiding as streaks and specks that once seemed unremarkable. Teams begin to search. One of the most important clues comes from the Vera Rubin Observatory, an ambitious survey telescope designed to map the entire southern sky in unprecedented detail. At the time 3I Atlas was discovered, the observatory is still in its commissioning phase, testing optics and operations, taking images to calibrate systems rather than to conduct full science surveys. Even so, its wide-field camera and deep exposures cover large swaths of the sky. When researchers reconstruct the past trajectory of 3I Atlas using the newly determined orbit, they realize that months before the discovery, the comet would have passed through fields that Rubin briefly observed. A focused search begins. Software combs through archived images, aligning them and subtracting static backgrounds to highlight moving sources. In one after another frame, faint linear features appear where no cataloged object should be, each one aligned with the predicted motion of the interstellar comet. In total, researchers identify several dozen pre-discovery detections, short streaks that trace the path of the object over a span of many nights. These archival points extend the observational arc backward, tightening the constraints on the orbit and confirming that 3I Atlas has been gliding inward on its hyperbolic path for months, without anyone knowing its significance. The thought that the comet was already present in those images, quietly recorded and stored before its special nature was recognized, adds a subtle layer of unease. It suggests that the sky is full of unnoticed travelers, visible yet unmarked, until a particular chain of events draws attention to them. Another line of evidence comes from a satellite that was not built with comets in mind at all. The Transiting Exoplanet Survey satellite, designed to detect dips in starlight caused by orbiting planets, continuously monitors wide strips of the sky for weeks at a time. Its cameras are sensitive enough to pick up faint moving objects that happen to cross their fields, though these objects are usually considered a form of noise for exoplanet studies. When the path of 3I Atlas is projected back into the time and pointing history of the satellite, it becomes clear that the comet passed through one of its monitored sectors during late spring of the same year. The satellite's continuous coverage means that instead of scattered still images, it may have captured an almost unbroken sequence of the comet's brightness as it moved. Investigators sift through the time series data, identifying a faint source that drifts systematically against the background star field. By stacking many exposures together and correcting for the comet's motion, they boost its signal above the noise, revealing a small extended patch rather than a pure point. This indicates that even at that early date, when the comet was still far from the sun, some level of activity had already begun. Ice on or near the surface was sublimating, releasing gas and dust to form a rudimentary coma. The satellite data allow estimates of the total brightness and, with assumptions about albedo, a refinement of the size estimate. Combined with the Rubin detections and ground-based follow-up, these observations narrow the likely diameter of the nucleus to somewhere around 5 to 6 kilometers, still with some uncertainty, but consistent with a large, dark body. The key point is that comet-like behavior is present when 3I Atlas is at a distance from the Sun where many ordinary comets would still be inert. At around 6 astronomical units, beyond the orbit of Jupiter, water ice alone is usually too cold to sublimate strongly. Activity at that distance hints at more volatile species, molecules that turn from solid to gas at lower temperatures, such as carbon dioxide or carbon monoxide. This early awakening will later be confirmed by infrared observations, but even at the archival stage, the clues are there in the faint extended profile and the timing of the brightening. The picture that emerges from these ghost traces is that 3I Atlas has been under watch longer than anyone initially realized. Survey instruments, both on the ground and in space, have been following its approach as part of their routine operations, capturing data that only later become significant. In the Rubin images, the comet appears as a faint, elongated smear, barely distinguishable from cosmic rays or minor defects. In the exoplanet satellites frames, it is a slowly moving spot that would be an annoyance in light curve analysis. Only after the orbit is known do these features cohere into the story of an interstellar comet already beginning to respond to solar radiation in the cold outskirts of the system. The process of hunting down these pre-discovery observations highlights the way modern astronomy operates. Detections made for one purpose can hold crucial information for entirely different questions, waiting in digital archives until someone asks the right query. Each successful recovery of 3I Atlas in earlier data extends the baseline over which its motion is measured, reducing the range of possible incoming directions and sharpening estimates of its passage through the galactic environment. The more precise the orbit, the better scientists can trace its path back through the galaxy and forward into interstellar space. This interplay between discovery and archive is not entirely new. Comets and asteroids have been located in older photographic plates before, yet, in the case of an interstellar object, the stakes feel higher. If such a body can hide in plain sight, despite its unusual path and speed, how many more have done the same, passing through the solar system at times when no suitable survey was operating, or when images were taken but never examined with this particular kind of search? Calculations suggest that interstellar objects of kilometer scale might pass through the inner solar system at rates of several per decade or more, depending on assumptions about how common such debris is in the galaxy. The fact that only a handful have been recognized so far hints that many have gone unnoticed. In this context, the Rubin and exoplanet satellite detections of 3I Atlas serve as both scientific gold and a reminder of limitations. They provide a unique extended view of the comet's inbound journey and early activity, yet they were only found because astronomers knew exactly where and when to look after the fact. As future surveys come online with greater depth and coverage, the hope is that more interstellar visitors will be caught earlier, tracked over longer arcs, and studied in greater detail, perhaps even in time for spacecraft to adjust trajectories for closer inspections. For now, the pre-discovery images of 3I Atlas transform the narrative of its encounter. It is no longer a sudden arrival, but a presence that has been quietly recorded over months, its faint image scattered across different telescopes and missions. Each recovered trace acts like a footprint in a long corridor that leads from the outer dark toward the inner regions of the solar system. The comet has passed through these corridors before anyone named it, leaving subtle imprints that only later eyes learn to see. This awareness brings a deepened sense of mystery. The solar system, once thought of as a largely closed arena of familiar objects, now appears as a crossroads where fragments from many stars may pass, sometimes noticed, often not. 3I Atlas becomes a symbol of this hidden traffic, a case where the archive itself offers a second chance to watch an alien object drawing near, its faint light already whispering clues about its nature, long before its name appears in any catalog. In that realization, the comet's quiet presence in those early images feels less like a coincidence and more like a sign of a broader, unseen pattern, one that will only become clearer as humanity learns to read the accumulated records of its own instruments with fresh questions in mind. As 3I Atlas continues its inward journey, the first clear signs of awakening unfold in the faint haze around its dark nucleus. Months before perihelion, when it still lies beyond the orbit of Jupiter, careful processing of archival images has already hinted that a diffuse envelope of gas and dust surrounds the solid core. At that distance, water ice alone should remain mostly inert, locked in a rigid state by the low solar flux. The presence of a visible coma at such a range suggests that more volatile substances are at work, materials that begin to sublimate under weaker sunlight. This early activity is subtle but persistent. As days and weeks pass and the comet draws closer to the sun, the coma steadily gains in brightness and extent. Ground-based telescopes with large apertures monitor it in visible light, while detectors in the near-infrared track the thermal glow of dust grains warmed by sunlight. Observers watch the coma expand from a tight halo only slightly larger than the instrumental point spread to a more extended cloud that fills the inner fields of view. Against the steady backgrounds of stars and galaxies, a small, fuzzy patch grows and sharpens, though the nucleus itself remains unresolved inside the glare. The surface of 3I Atlas, once bathed only in the weak radiation of distant stars, now begins to experience a rising flux of solar energy, and the buried or exposed ices respond. In this phase, the comet remains an unresolved point for most instruments, but space-based observatories with higher angular resolution provide a clearer view. The Hubble Space Telescope, with its sharp optics above the blur of Earth's atmosphere, turns toward the interstellar visitor when it is still several astronomical units from its closest approach to the Sun. Images taken through multiple filters reveal a compact central condensation surrounded by a smooth coma that extends over many thousands of kilometers. Careful modeling of the brightness profile allows astronomers to estimate how much material is streaming off the nucleus. They derive mass loss rates ranging from a little more than a dozen kilograms per second to roughly an order of magnitude higher, depending on assumptions about dust sizes and gas composition. These numbers are modest by the standards of some near-perihelion comets, but significant for an object still in the outer solar system. The engine driving this activity is already strong, yet the surface temperature remains too low for water alone to explain it. Along with the symmetric coma, Hubble images show something more unexpected. There appears to be a concentrated feature extending not away from the Sun, as one would expect for a typical dust tail shaped by radiation pressure and the solar wind, but roughly toward it. This structure resembles an anti-tail, an apparent dust feature that seems to point sunward rather than anti-solar. In many comets, anti-tails arise from projection effects, where a sheet of dust lying in the comet's orbital plane is viewed from a particular angle such that it appears to extend in a counterintuitive direction. In the case of 3I Atlas, the presence of such a feature at a time when the comet is still relatively far from the Sun raises questions about the dynamics of its dust environment. Particle size distributions, ejection velocities, and the interplay of solar radiation pressure with gravity all shape how dust is arranged in space. For the observed geometry to produce a sunward-pointing feature, grains must have particular combinations of size and velocity, lifted off the nucleus and then guided into a sheet that intersects the line of sight in a specific way. Models of this configuration show that relatively large, slow-moving dust grains could remain near the orbital plane, while smaller particles are pushed more rapidly into conventional tails. The anti-tail thus hints at a complex distribution of dust sizes and ejection patterns, perhaps tied to localized regions of activity on the nucleus. Even as these structures form, the solar wind at these distances remains too weak to dominate, so the radiation field becomes the primary sculptor of the coma. Hubble observations also refine the estimate of the nucleus size. By separating the contribution of the coma from the unresolved core and assuming a low reflectivity consistent with the object's color, astronomers converge on a diameter of roughly 5.5 kilometers, with uncertainties tied to the exact albedo and dust contamination. This value aligns with estimates from archival survey and exoplanet satellite data, reinforcing the picture of a relatively large interstellar comet. A body of this scale possesses significant thermal inertia, meaning that as its surface layers warm and cool, their response is smoothed over time and depth. This inertia can affect how and when different volatile components sublimate, further complicating the evolution of the coma and tails. Around the same period, other observatories report variations in the appearance of the surrounding halo that may be tied to transient space weather. Solar monitors record a coronal mass ejection, a burst of charged particles and magnetic field launched from the Sun, passing through the region near the comet's path. Some speculate that this event could alter the structure of the coma, compressing it or generating subtle changes in the distribution of ions and dust. However, early analyses suggest that any such impact is minor compared with the broader thermal driving of activity. The nucleus continues to shed material at roughly consistent rates, and no catastrophic disruption or dramatic change is observed. The comet persists as a stable, steadily breathing object, exhaling gas and dust in a controlled way, rather than in violent outbursts. As 3I Atlas approaches the inner solar system, ground-based telescopes begin to resolve a faint tail extending away from the nucleus. Initially, this tail is extremely short, detectable only in deep exposures and careful image processing. Observers report that on a particular date in early September, a clear dust tail appears, spanning a small fraction of a degree on the sky. At that time, only the largest telescopes with excellent atmospheric conditions can trace it, but its presence confirms that the comet now carries a visible signature of its motion through the solar radiation field. Dust grains, once part of the surface, now drift behind the nucleus along its orbit, forming a narrow band lit by the Sun. The coexistence of a conventional tail and a sunward-facing feature reinforces the sense that 3I Atlas does not behave quite like a typical short-period comet. The relative strengths and shapes of these structures shift with time as activity levels change and viewing geometry evolves. Somewhere in the complex interplay of gas drag, rotation, and solar pressure lies the explanation for why this interstellar object displays both familiar and unusual features. The pattern of activity as a function of distance also stands out. When compared with the second interstellar comet, which followed a more traditional brightness curve rising steeply as it neared the Sun, 3I Atlas brightens earlier and maintains a somewhat different relationship between heliocentric distance and outgassing rate. This difference suggests that the mix of volatiles is not the same. that the ratios of drivers like carbon dioxide and carbon monoxide to water are shifted in favor of species that function more efficiently in the cold. Later infrared observations will confirm this impression, revealing a coma dominated by carbon dioxide, with an unusually high ratio of carbon dioxide to water. For now, even in the visible and near-infrared bands, the early onset of activity and the persistence of the coma at large distances act as a strong hint that this comet carries a volatile inventory distinct from most solar system examples. Taken together, the observations in this phase transform 3I Atlas from a dark, turning nucleus into a fully fledged comet, surrounded by a growing atmosphere and trailing dust structures that respond to the sun in both expected and surprising ways. The numbers attached to the coma and tail tell part of the story. Mass loss rates measured in tens of kilograms each second, tail lengths that stretch from barely resolved smudges to larger fans, dust grains of varying sizes occupying different dynamical regimes. Yet, behind these measurements lies a deeper mystery about the object's internal layering and composition. How are ices distributed beneath the surface? Which regions activate first as sunlight penetrates? And why do they produce the specific patterns seen in the coma? For an interstellar body that has wandered through darkness for longer than the solar system has existed, the first touch of sustained solar warmth is both a scientific probe and a one-time event. The outer layers, processed for ages by cosmic radiation, now erode away, revealing materials that may have been buried since the time of its formation around another star. The coma becomes a temporary laboratory, an expanding shell that carries a sample of that interior into space where telescopes and spectrographs can dissect it from afar. In that sense, every dust grain and molecule escaping 3I Atlas during this awakening phase is a data point from a distant planetary system, encoded not only in its chemistry, but in the manner and timing of its release. The details of the antitail, the rate at which the coma turns on, and the stability of the mass loss all feed into this picture, suggesting that beneath the simple term comet lies a complex history of formation, ejection, and interstellar travel that shaped how this ancient fragment now responds to the sun. When the James Webb Space Telescope turns its mirrors toward 3I Atlas, the comet has already revealed much about its size, color, and activity. Yet its true distinctiveness lies in what its light carries in the infrared. Where visible light tells astronomers how the surface and dust reflect sunlight, infrared spectra reveal the fingerprints of specific molecules in the gas surrounding the nucleus. For a comet that formed around another star, this inventory is not just a list of constituents. It is a record of the physical conditions in its birthplace, encoded in abundances and ratios that cannot easily be reproduced by later processing. Webb observes the interstellar comet when it is still several astronomical units from the sun, a regime where many solar system comets are only beginning to stir. Its instruments disperse the incoming infrared light, spreading it into detailed spectra. In these spectra, familiar features emerge. Emission from water vapor appears as expected, signaling that some water ice is sublimating from the surface or from freshly exposed layers. However, the lines associated with carbon dioxide stand out with unusual strength. By comparing the intensities of these features and modeling the radiative transfer, researchers estimate that the coma of 3I Atlas is dominated by carbon dioxide gas, with a ratio of carbon dioxide to water that is strikingly high. Where many comets display carbon dioxide as a secondary component, here it seems to outweigh water by a factor of several, perhaps on the order of 7 or 8 to 1. The exact value varies with the details of the analysis, but the trend is unmistakable. This is a carbon dioxide-rich comet in a way that has rarely, if ever, been seen in the solar system. This dominance of carbon dioxide is more than a curiosity. It suggests that the original ices that condensed to form the nucleus accumulated under conditions where carbon dioxide was abundant and stable, while water did not dominate in the same way. In protoplanetary disks, the distribution of different ices is governed by frost lines, also called snow lines, distances from the central star where particular volatile substances can remain solid rather than evaporate. Closer to the star, temperatures are high, and most volatiles cannot condense. Farther out, temperatures drop, and more species can freeze onto dust grains. In the solar system, the water frost line lies near the middle of the asteroid belt. Inside this distance, rocky planets form from mostly dry material. Beyond it, water ice plays a major role in building the cores of giant planets and the icy bodies that populate the outer regions. Still farther out, a carbon dioxide frost line exists where even carbon dioxide can remain frozen on grains, shaping the composition of objects that form there. The infrared signature of 3I Atlas points toward a birthplace near such a carbon dioxide frost line, not in the inner reaches of a disk where water dominates, nor in the extreme outer darkness where other volatile species prevail, but in an intermediate zone where carbon dioxide ice is both plentiful and stable over long timescales. This is a place that has no exact analog in the modern solar system's known populations, at least not among objects that come regularly into view. Comets that visit from the distant Oort cloud and Kuiper belt show a range of compositions, yet few present such a consistently high proportion of carbon dioxide to water. The difference suggests that the protoplanetary disk where 3I Atlas formed may have had a different temperature structure, pressure profile, or chemical evolution. Perhaps its central star emitted a different spectrum of radiation, shifting the frost lines inward or outward. Perhaps the disk's density and turbulence created local pockets where carbon dioxide could condense more efficiently. Alternatively, the comet's present composition might result from strong processing after formation, such as preferential loss of water ice during long exposure to interstellar radiation, leaving behind a residue enriched in carbon dioxide. Each of these scenarios carries implications for how planetesimals evolve in different stellar environments, and the true explanation may involve a combination of formation and alteration over immense timescales. Webb spectra do not only reveal carbon dioxide. They also show hints of other species, including carbon monoxide and fragments of more complex organics, though disentangling these features is challenging. The clarity of the carbon dioxide lines, however, makes them a central anchor for models of the comet's interior. If the coma is dominated by this gas, even at distances where water is barely active, then the upper layers of the nucleus must contain substantial reservoirs of carbon dioxide ice, perhaps in pockets or layers beneath a dark, insulating crust. As solar heat penetrates, these reservoirs vent gas through fractures and pores, dragging dust into space and building the observed coma and tail. The pattern of activity observed at different distances supports this picture. When 3I Atlas is still far from the Sun, its brightness rises more quickly than would be expected if water were the primary driver. As it comes closer, the rate of increase follows a curve that aligns better with models where carbon dioxide dominates at large distances and water contributes more only in the inner region. This layered behavior hints at stratification within the nucleus, possibly recording different phases of growth in the original disk. Thin crusts of processed material may overlay more pristine interior regions, with certain volatile rich bands activating at specific thermal thresholds. The idea of a carbon dioxide frost line in another system invites comparison with the solar system's own structure. If 3I Atlas formed near such a line, it likely occupied a region where gas giants or ice giants might also have taken shape, drawing in similar materials. In that case, the comet could be a leftover fragment from the same reservoir that built larger worlds, thrown outward by gravitational encounters during the early chaotic phases of planetary migration. Numerical simulations of planet formation suggest that such scattering events are common. Young giant planets can hurl planetesimals both inward, feeding inner planet formation, and outward, populating distant clouds of debris, and even ejecting objects entirely from the system. 3I Atlas may thus be a tiny emissary from a zone where giant planets once moved, carrying in its ices a record of that architecturally important region. Another way to frame the same data is to note how different the comet is from typical carbon dioxide content in solar system comets. In many comets studied near Earth's orbit, water vapor dominates the gas output, with carbon dioxide making up a smaller fraction. Some exceptions exist, but the magnitude of the imbalance in 3I Atlas stands out. This difference could be a matter of initial conditions in the parent disk, sensitivity to local chemical equilibria that shaped how carbon dioxide and water were partitioned. It could also reflect broader galactic context. A star born in a metal-poor region of the Milky Way, where heavy elements are scarcer, might produce disks with different relative abundances of carbon, oxygen, nitrogen, and other building blocks. If 3I Atlas indeed originated in the thick disk of the galaxy, as later dynamical studies suggest, then its unusual carbon dioxide richness might be a chemical echo of that environment, reflecting a balance between volatile species that diverges from the solar neighborhood norm. The infrared spectrum becomes, in this sense, a bridge between small-scale and large-scale. A handful of gas lines in the coma tell a story that ranges from the microphysics of sublimation on a sunlit surface to the macroscopic history of star formation and chemical enrichment in the galaxy. Even with these insights, many questions remain. How uniform is the carbon dioxide abundance across the nucleus? Are there localized vents rich in this gas, or is it broadly distributed? Does the high ratio persist throughout the comet's passage, Or does it evolve as different layers are exposed? Answering these questions requires repeated observations at multiple points along the orbit, something that missions like Webb and other space-based telescopes attempt, as scheduling and visibility allow. Each visit samples a different slice of the comet's thermal history, turning the single fly-through of the solar system into a sequence of experimental conditions. The broader implication is that interstellar comets like 3I Atlas are not just oddities, but probes of planetary chemistry beyond the solar system. Where exoplanet atmospheres provide information about giant gaseous worlds and debris disks trace dust in young systems, a solid icy nucleus that has been ejected and later encountered offers a direct sample of solid phase chemistry. For now, that sample is only accessible through the gas it releases as it warms, but in future, missions may attempt to fly close enough to taste the coma directly, or even collect and return dust grains. In anticipation of that era, the detailed spectra from Webb and other observatories act as a template. They show how an interstellar comet can differ from local ones in specific, quantifiable ways, such as a carbon dioxide to water ratio far outside familiar ranges. They also illustrate how those differences can be interpreted in terms of frost lines, disk structures, and galactic environments. In the case of 3I Atlas, the message carried in its gas is clear yet enigmatic. It was born where carbon dioxide could freeze in abundance and remain stable for long enough to be locked into a growing nucleus, in a region of space and time that the solar system never occupied. The precise circumstances remain out of reach, but the comet's chemistry marks it as an artifact of a distant, cold threshold, a frozen contour in another system's map that now briefly intersects the sun's domain. Metals in the interstellar mist first make themselves known not through shining veins on a photographed surface, but through faint lines in a spectrum, thin markers that appear when atoms or ions in the coma absorb or emit light at very specific wavelengths. As 3I Atlas approaches the inner solar system and its activity strengthens, astronomers use large, ground-based telescopes equipped with high-resolution spectrographs to dissect the light coming from its surrounding gas. Among these instruments, the Very Large Telescope in the Southern Hemisphere plays a central role. Its mirrors collect the dim glow of the coma and tail, feeding it into a spectrograph that spreads the light into a finely detailed rainbow. Against this spread, individual features stand out as peaks or dips, each corresponding to a particular transition in a specific species. When the data are carefully calibrated and compared with laboratory references, an unexpected pattern emerges. There are clear signatures of nickel present in the gas around the comet, yet comparable signatures of iron, a chemically similar and usually abundant metal, are not seen at the same levels. The presence of nickel in the coma is surprising because the temperatures and distances involved should not allow metallic elements to sublimate directly from the surface as pure atoms or simple molecules. Nickel, like iron, usually resides in the refractory part of a comet, locked into minerals and metal-rich grains that require high heat to vaporize. Near the distance where 3I Atlas is observed, the sunlight is not intense enough to liberate these metals if they are bound in ordinary rocks or alloys. The spectra therefore suggest that the nickel is being released through a different pathway. The most plausible explanation is that it is carried into the coma as part of more volatile complexes, perhaps organometallic compounds, or tiny grains coated with organic material that sublimate at lower temperatures. As these carriers are lifted off the surface by escaping gas and exposed to ultraviolet light and particle radiation, they break apart, freeing nickel atoms or ions that then reveal themselves in the spectral lines. The absence of strong iron signatures points to a composition in which nickel is more efficiently bound into such releasable forms, or to subtle differences in how iron and nickel are distributed within the surface layers. This imbalance does not necessarily mean that the comet lacks iron overall. It could simply reflect that, under the specific conditions of this passage, nickel has more accessible pathways from the solid phase into the gas, while iron remains mostly trapped in the dust grains that continue to follow the nucleus along its orbit. Alongside the metal lines, the spectra also show clear evidence of cyanide radicals. These features are familiar from studies of many comets within the solar system. Cyanide, a molecule composed of carbon and nitrogen, forms readily in cometary comae as parent molecules such as hydrogen cyanide are dissociated by ultraviolet light. Its detection in 3I Atlas therefore does not by itself mark the comet as unusual, but it connects this interstellar visitor to a long history of comet observations. More than a century ago, when astronomers first began to identify cyanide in the spectra of comets like Halley, public audiences were unsettled by the idea that a toxic gas might be present in a passing tail. In practice, the densities are far too low to pose any threat to planets, yet the association of comets with exotic and sometimes hazardous chemistry has persisted. In the case of 3I Atlas, cyanide joins carbon dioxide, water, and other species as part of a complex chemical environment shaped by inherited ices and by processing during the comet's approach to the Sun. The combination of nickel in the gas phase, a high carbon dioxide to water ratio, and a dark, reddish dust population invites comparisons with rare meteorites found on Earth. The Tagish Lake meteorite, for example, is known for its primitive composition, including organic material and fine-grained carbon-rich phases. Spectroscopic studies of that meteorite and similar samples show absorption features and elemental abundances that bear some resemblance to what is inferred for 3I Atlas. While it would be premature to claim a direct match, the analogy suggests that the comet's nucleus might contain metal-bearing organics and finely mixed metals and silicates, all embedded in a matrix that formed at low temperatures in a chemically rich environment. If nickel is preferentially incorporated into certain organic or sulfide phases that are more volatile than typical silicate minerals, it could explain why nickel lines appear in the coma while iron remains largely absent. At the same time, the broader galactic context cannot be ignored. Dynamical studies of 3I Atlas indicate that its incoming trajectory is consistent with an origin in the thick disk of the Milky Way, a component of the galaxy composed of older, more metal-poor stars than those in the thin disk where the Sun resides. In such environments, the overall abundance of heavy elements is lower, and the relative ratios of different metals can differ from solar values. A body that forms in a metal-poor disk might naturally have a different balance of iron, nickel, and other elements in its minerals. Over billions of years, exposure to cosmic rays and interstellar radiation fields could further modify surface layers, selectively altering some compounds while leaving others intact. The spectroscopic signature of nickel without strong iron may therefore reflect both the initial conditions of formation and the long journey through a different galactic neighborhood. To probe these possibilities, researchers develop models that simulate how various mixtures of minerals and organics respond to heating and irradiation. In these models, grains containing nickel bound in certain complexes begin to release nickel-bearing species at temperatures reached by 3I Atlas along its trajectory, while iron remains sequestered. Ultraviolet photons can liberate metal atoms from excited complexes, and sputtering by energetic particles can knock atoms from grain surfaces. Chemical reactions in the coma, driven by sunlight, may also play a role in transforming parent species into the forms detected. The goal of these models is not to pin down a single definitive composition, but to explore which combinations of starting materials and processes can reproduce the observed line strengths. Even within this framework, the case of 3I Atlas appears to require unusually efficient pathways for nickel to enter the gas. The presence of nickel lines at relatively large heliocentric distances indicates that the responsible carriers are not extremely refractory. They must begin to break down in conditions that are still cold by terrestrial standards. This requirement fits with the idea of an interstellar comet rich in complex organics and low-temperature condensates, formed beyond a carbon dioxide frost line where ices collect in thick mantles on grains. In such a setting, metals might become trapped in amorphous ice matrices or in coatings that release them gradually as the comet warms, rather than remaining locked in deep, crystalline cores. There is also the question of how these metals might have been distributed during the early stages of the parent disk's evolution. In protoplanetary disks, radial and vertical mixing can carry grains through regions of varying temperature and pressure, potentially leading to fractionation between different metals and volatile carriers. If nickel-bearing grains experienced slightly different transport histories than iron-rich grains, they could end up in different reservoirs before being incorporated into planetesimals. 3I Atlas, as one such planetesimal ejected from its system, would then carry a record of those differences frozen into its structure. In this view, the nickel lines in its coma are not just markers of present outgassing, but relics of accretion and migration processes around another star. The detection of cyanide alongside these metals adds another layer. Cyanide and related molecules are key intermediates in many pathways that form more complex organics in both interstellar clouds and protoplanetary disks. Their presence in the coma of 3I Atlas confirms that the comet holds nitrogen-bearing organics that respond actively to solar ultraviolet radiation. The relative strengths of cyanide features compared with other nitrogen species can, in principle, reveal how nitrogen was partitioned in the original disk and how much has been lost or transformed over time. Combined with the metal lines, the cyanide signals suggest a rich interplay between inorganic and organic chemistry, where metals may catalyze reactions on grain surfaces or within ice matrices, leaving subtle fingerprints in the coma's composition. These various strands of evidence converge on a picture of 3I Atlas as a chemically intricate object whose surface layers act as a kind of interstellar laboratory. The metals in its mist do not point straightforwardly to exposed veins or molten flows, but to delicate processes of release from complex hosts. They demonstrate that even at large distances, where temperatures are low, the combination of solar radiation, outgassing, and prior cosmic processing can mobilize species that would seem, at first glance, to be immobile. At the same time, the absence of iron in the gas phase reminds scientists that observations always see only part of the whole. The bulk of the comet's metal content remains hidden in dust grains and deeper layers, still locked away from spectrographs that can only measure what has escaped. The mystery lies not only in what is seen, but in what is missing. Iron, so common in planetary cores and meteorites, is spectroscopically quiet here, while nickel, usually a companion, speaks clearly. Whether this difference is a quirk of the present passage, a diagnostic of the comet's birthplace, or a sign of deeper chemical patterns in other systems is not yet known. In future, more interstellar comets will offer points of comparison. Some may show both nickel and iron in their comae, others perhaps neither. For now, 3I Atlas stands as an example in which metals appear in unexpected proportions, hinting that the diversity of solid chemistry beyond the solar system is at least as rich as that within it. The thin spectral lines from its coma thus become threads connecting laboratory experiments, meteorite studies, disk models, and galactic archaeology, all woven together in the effort to understand how a small, dark traveler can carry in its gas such suggestive traces of another world's long-vanished nebula. The path that 3I Atlas follows through the solar system is only a small segment of its full journey. Once the orbit is well constrained by months of astrometric data, dynamicists turn their attention outward, using the measured incoming speed and direction to trace the comet's motion back through the larger gravitational field of the galaxy. The Sun is not isolated. It orbits the Milky Way within a vast distribution of stars, gas, and dark matter, and its gravity well is only a local perturbation on that broader potential. An interstellar object arriving on a hyperbolic trajectory carries in its velocity vector the imprint of where it has been in this larger structure. By combining the comet's present motion relative to the Sun with models of the galactic gravitational field, researchers integrate its trajectory backward in time, following it out of the solar neighborhood and into the wider Milky Way. They also account for the motion of nearby stars, whose own gravity may have nudged the comet's course over millions of years. In these numerical experiments, 3I Atlas emerges from a region associated with what astronomers call the thick disk of the galaxy, a component composed primarily of older, more metal-poor stars than those typical of the thin disk where the Sun resides. Thick disk stars tend to have higher vertical velocities and occupy orbits that carry them farther above and below the galactic plane. The comet's reconstructed incoming direction and speed match well with what would be expected for a body born in this environment and later scattered into interstellar space. One early analysis focuses on whether close stellar encounters could have significantly altered the comet's trajectory along the way. By combining catalogs of stellar positions and motions with the integrated path of 3I Atlas, the team identifies dozens of instances over the last several million years when the comet and a star pass within a few light-years of each other. Each encounter is evaluated for its gravitational influence. The closer the two objects come and the slower their relative speed, the more strongly the star can deflect the comet. In the case of 3I Atlas, however, the closest identified approach is on the order of 1/3 of a light-year. Still far enough that the change in velocity is calculated to be only a small fraction of a meter per second. Over timescales of 10 million years, the cumulative effect of many such weak perturbations remains negligible compared with the comet's overall galactic motion. This finding is crucial. It means that the velocity vector with which 3I Atlas enters the solar system has not been heavily scrambled by recent close stellar flybys. Instead, it largely preserves the memory of its origin in the thick disk and of the initial ejection event that cast it into interstellar space. With this confidence, researchers push their models further back. They consider not just the recent few million years, but the broader age implied by the comet's kinematics and its likely parent population. Thick disk stars are among the older members of the galaxy, with ages often measured in several billions of years. If 3I Atlas formed along with such a star, then its solid material may date back to a time when the Milky Way was younger and less enriched in heavy elements than it is now. On this basis, estimates of the comet's age range from roughly 3 to more than 10 billion years. The uncertainty is large because neither the precise formation time of its parent star nor the exact epoch of ejection is known. Yet even the lower end of this range makes the comet older than the Sun and all the planets. In other words, 3I Atlas may be the oldest physical object ever observed passing through the solar system, carrying in its structure a history that begins well before the solar nebula collapsed. This temporal perspective reframes the comet. It is no longer simply a visitor from another planetary system, but a remnant from a much earlier era in the galaxy's evolution. The thick disk in which it likely formed had different chemical abundances and dynamical conditions from the thin disk that later produced the Sun. Metallicity, the measure of how many elements heavier than helium are present, tends to be lower in thick disk stars. This means that the proportion of materials like iron, nickel, silicon, and oxygen available for planet formation was different, as were the relative abundances of key volatile elements such as carbon and nitrogen. The unusual composition of 3I Atlas, particularly its high carbon dioxide to water ratio and the peculiar behavior of metals in its coma, fits within this context. A protoplanetary disk in a metal-poor environment might naturally produce planetesimals with different volatile mixtures and mineral balances. The carbon dioxide frost line around such a star could lie at a different distance relative to regions where giant planets form, and the interplay of radiation and disk chemistry could favor the incorporation of carbon dioxide ice into growing bodies in ways that do not occur in the solar system. In this sense, the comet's chemistry and its dynamical origin reinforce each other, both pointing toward a birthplace in an old, low metallicity region of the galaxy. To get from that birthplace to the present hyperbolic passage, the comet must at some point have been ejected from its parent system. The likely mechanism involves gravitational interactions with massive planets or with other large bodies during the system's early evolution. In young planetary systems, giant planets can migrate through the surrounding disk, scattering planetesimals in all directions. Some are sent inward, where they may collide with forming terrestrial planets or be vaporized in the inner regions. Others are thrown outward into distant reservoirs, analogous to the solar system's Oort cloud. A fraction of these are imparted with enough energy to escape entirely, becoming free-floating objects in interstellar space. 3I Atlas is one such fragment, cast out after its system's architecture settled, but long before the Sun formed. Once in interstellar space, its motion is governed primarily by the smooth gravitational field of the Milky Way, punctuated by the weak tugs of distant passing stars and giant molecular clouds. Over billions of years, it follows an orbit around the galactic center that is only loosely coupled to the paths of any particular stars. The comet's present velocity relative to the Sun is the result of this long wandering integrated over cosmic time. The fact that it now intersects the solar system is an outcome of that wandering and of the Sun's own motion through the galaxy, not of any special alignment or attraction. Yet for the observers who study it, this encounter is not just one more random crossing. It is an opportunity to sample material from an era and environment otherwise accessible only through indirect observations of distant stars and gas clouds. Galactic archaeologists, scientists who reconstruct the history of the Milky Way by studying the properties of its stellar populations, usually rely on spectroscopy of stars and on surveys of star clusters and streams. 3. iAtlas adds a different kind of evidence, a small, solid witness drawn from the thick disk, carrying in its ices and dust a record of conditions in that early population. When dynamicists compute the forward trajectory of the comet after it leaves the solar system, they find that it will continue to orbit the galaxy for eons, its path altered only slightly by encounters with other stars and by the overall evolution of the galactic potential. The brief bending of its track by the Sun is a tiny perturbation on an orbit that spans tens of thousands of light years. In future, long after the solar system itself has changed, 3I Atlas will pass near other stars, perhaps grazing the edges of other planetary systems as an unremarkable small body among many. There is a certain asymmetry in this picture. For the comet, the passage through the solar system is just one more minor event in a very long existence. For the solar system, especially for the scientific civilization that happens to be watching, that same passage is a unique chance to examine an ancient fragment under relatively favorable conditions. This asymmetry underscores how the interpretation of such encounters depends on perspective. From an objective standpoint, millions of similar interstellar objects likely wander the galaxy at any given time, products of countless planetary systems and scattering events. Only a tiny fraction will ever pass through the narrow column of space in which a technological species has both the tools and the interest to observe them in detail. That 3-eye atlas happens to be one of them, and that it does so at a time when sensitive telescopes, both on Earth and in space, are available, is the contingent part of an otherwise generic story. The idea that this comet may be older than the Sun also challenges intuitive notions of planetary time. In the usual view, comets in the solar system are ancient because they preserve icy material from the earliest phases of planet formation here, dating back 4.5 billion years. They already seem to carry deep time. 3-eye atlas extends that timescale further. If its age truly lies somewhere between 3 and 11 billion years, then it has existed through multiple major phases of the Milky Way's life. It may have formed at a time when the rate of star formation in the galaxy was higher, when the thick disk was still settling, and when the overall metallicity was substantially lower. It has seen spiral arms come and go, giant molecular clouds disperse, and perhaps even minor mergers reshape the galactic structure, all while remaining a small, dark body wandering mostly unnoticed. This long history does not leave visible marks in the way that erosion or tectonics might on a planet, but it may leave subtle imprints in cosmic ray damage tracks, isotopic ratios, and the distribution of trapped gases. Some of these could, in principle, be inferred from high-precision spectroscopy of the coma. Others would require direct sampling, something far beyond current capabilities for an object on such a fast, hyperbolic path. Still, the recognition that such records exist within 3-eye atlas turns it into a kind of time capsule. Not a pristine one, because its surface has been altered by the very processes that expose its interior now, but one that nevertheless carries traces of conditions that no longer prevail in most parts of the galaxy. As more interstellar comets are discovered, patterns may emerge. Some may point back to the thin disk, others to the halo, or to disrupted dwarf galaxies. Each will carry its own combination of kinematic and chemical signatures. For now, 3-eye atlas stands as one of the first clear examples where those signatures align to tell a coherent story. A large, dark, carbon dioxide-rich nucleus, likely formed in a metal-poor, thick disk environment billions of years before the solar system existed, ejected into interstellar space by planetary dynamics, and now briefly illuminated by the Sun before fading again into the wider Milky Way. Its age is written not in inscriptions or surface features, but in its motion through space, and its composition, both of which tie it to epochs and regions that humans can otherwise only infer. The mystery that remains is how fully such a small object can truly encode the vast history it has lived through. The answer may lie in the comparison with future visitors, and in the continued refinement of models that link galactic evolution, disk chemistry, and planetesimal physics. 3. iAtlas offers a first, tantalizing data point in this new kind of galactic archaeology, one in which comets serve as ancient shards of worlds long gone, moving silently between stars and occasionally passing close enough to be seen. As 3-eye atlas threads its way through the inner solar system, the focus of study shifts from distant observatories to a scattered network of spacecraft, each with its own vantage point and limitations. The comet's calculated trajectory shows that in early October, it passes relatively near Mars, at a distance that is small on planetary scales, yet still tens of millions of kilometers away. Even at that separation, the encounter is close enough that cameras on and around the red planet can attempt to capture the interstellar visitor against the Martian sky. Mission planners identify time windows when the comet climbs above the horizon from the perspective of rovers on the surface and passes through the pointing constraints of orbiters overhead. The timing coincides, however, with a shutdown in major United States government operations, constraining the ability of some mission teams to schedule special observations or process new data. Despite this, the Perseverance rover on the floor of Jezero crater manages to carry out a series of long sky exposures on the designated night. Its cameras, usually dedicated to mapping rocks and dust, turn upward and stare at the thin Martian atmosphere, integrating faint light from stars, dust, and, hidden among them, the moving point of 3-eye atlas. The raw frames show little at first glance, just speckled noise and streaks from cosmic rays. Only after patient stacking and alignment by dedicated analysts does the comet emerge as a tiny elongation, a slight enhancement that shifts from frame to frame in a way that matches the predicted motion. From the surface of another world, an interstellar object is recorded as it passes overhead, a meeting of two stories that both began around different stars. In orbit around Mars, other spacecraft attempt similar feats. The trace gas orbiter of the ExoMars mission, equipped with instruments designed to study the Martian atmosphere, repurposes its cameras to observe 3I Atlas during several days around closest approach. Short exposures accumulate as the comet moves through its field of view. By combining these into deep stacks and subtracting out the fixed stars, mission scientists produce images that show a faint, slightly extended source, brighter than a single point and accompanied by a minuscule tail aligned roughly along the comet's trajectory. Though the spacecraft was never optimized for such distant, dim targets, its position above the Martian atmosphere gives it a clear, stable platform. The resulting images demonstrate how even instruments designed for planet-focused science can contribute to the study of transient interstellar visitors when geometry and opportunity align. Another orbiter, Mars Express, also turns its camera toward the region where the comet should appear. Its optics and detectors, tuned for imaging the Martian surface and its small moons, can only take relatively brief exposures. These short integrations make detection more challenging, and early reports suggest that any signal from the comet remains buried in noise. Nonetheless, the attempts add to the sense of a multi-mission effort, a set of eyes distributed around a planet, all seeking traces of a fleeting object between the stars. The Mars Reconnaissance Orbiter, with its powerful high-resolution camera, is in principle the most capable platform for imaging the comet's nucleus from Mars orbit. Its half-meter class telescope has captured detailed views of surface features and even hardware on the Martian ground. Yet, because of operational constraints linked to the governmental pause, special targeting for 3I Atlas is delayed. For a time, those images exist only as possibilities, their eventual retrieval contingent on administrative circumstances beyond the control of the comet or the instruments. This intersection between celestial mechanics and human systems forms an odd contrast. An ancient interstellar body moves with precise predictability, while the ability to observe it depends on contemporary politics and institutional schedules. Beyond Mars, other spacecraft prepare for more distant encounters. The geometry of the comet's orbit, which carries it behind the Sun from Earth's point of view around the time of its closest approach, means that ground-based telescopes on Earth enter a period when direct observation is impossible. The glare of the solar corona and the dangerous proximity to the Sun's disk prevent optical instruments from following the comet as it sweeps through its most active phase. However, spacecraft positioned elsewhere in the solar system enjoy different lines of sight. One such platform is a mission of the European Space Agency exploring the outer planets. As 3I Atlas approaches perihelion on the far side of the Sun from Earth, this spacecraft finds itself in a configuration where the comet is visible against the dark backdrop of space, rather than lost in solar glare. Instruments that normally monitor the environment around a distant gas giant or measure its moons pivot temporarily to track the dim, fast-moving target. At these distances, the comet's coma is more extended and its tail longer, shaped by weeks of outgassing near peak heating. The spacecraft's cameras capture a perspective that no Earthbound facility can match, revealing the full length of the dust and gas structures as they stream away from the nucleus under the influence of sunlight and the solar wind. Simultaneously, radio and plasma instruments on the same mission monitor subtle changes in the charged particle environment as the spacecraft passes through or near the outskirts of the comet's tail. Even if the local density of ions and dust remains low, small perturbations in magnetic fields and plasma flows may betray the presence of cometary material. Detecting such changes is challenging, requiring careful separation of comet-related signals from the ever-shifting background of the heliosphere. Yet, the attempt offers a preview of future dedicated fly-through missions. Later, as 3I Atlas continues outward on its post-perihelion leg, the alignment with Jupiter brings the Juno spacecraft into a position to observe from yet another angle. Juno, tasked primarily with mapping the giant planet's gravity field, magnetic field, and auroras, is not optimized for distant comet imaging, but its instruments are capable of sensing diffuse structures in radiative environments. From its vantage point near Jupiter's polar regions, the spacecraft can look outward toward the incoming or outgoing comet and record the brightness of its coma and tail at wavelengths that complement those accessible from Earth. The distance between Juno and 3I Atlas remains large, so the comet appears as a faint smear rather than a resolved structure. But its presence allows scientists to cross-calibrate models of cometary brightness with measurements taken earlier from near Earth and Mars. These distributed observations, gathered by missions that were each designed with different primary goals, turn the passage of 3I Atlas into an unplanned, coordinated campaign. Earth-based telescopes provide high-resolution spectra and detailed light curves during the inbound phase and after the comet re-emerges from behind the Sun. Mars missions offer side views near one planetary flyby, capturing the interstellar visitor in a foreign sky. Distant spacecraft contribute unique perspectives during periods when Earth is geometrically blind. Together, they map the comet's activity and morphology as functions of both distance from the Sun and viewing angle. This patchwork coverage reveals patterns and asymmetries that a single observer could easily miss. For example, changes in tail structure seen from Mars may align with shifts in gas production rates measured from Earth, helping to separate intrinsic variability from geometric projection effects. Observations from different heliocentric longitudes also allow studies of how the solar wind and interplanetary magnetic field shape the ion tail over time. The comet's interaction with these fields varies as it moves through regions of differing solar wind speed and density. Spacecraft measurements of local plasma conditions can be paired with remote imaging of tail kinks, disconnections, or waves, building a fuller picture of how an interstellar nucleus responds to a star's extended atmosphere. Beyond the immediate scientific return, the multi-vantage study of 3I Atlas serves as a rehearsal for future purpose-built missions. The European Space Agency's Comet Interceptor, planned to wait in a quasi-stable orbit until a suitable target is discovered, embodies this new approach. Instead of designing missions around specific, long-known comets from the solar system's own reservoirs, planners now consider the possibility that an interstellar object might present itself with enough warning to justify a rapid intercept. The experience with 3I Atlas shows both the promise and the difficulty of this strategy. On the one hand, early recognition of an interstellar trajectory enables coordinated observations from many platforms. On the other, the high inbound speed and unpredictable timing of such discoveries make it challenging to position spacecraft for close flybys. In the case of 3I Atlas, no spacecraft is in the right place at the right time for a close pass by the nucleus itself. All views remain remote, mediated by long lines of sight and partial coverage. Yet the very act of repurposing existing missions demonstrates the flexibility of a solar system saturated with robotic explorers. It shows that when an object of special interest appears, spacecraft originally built for other goals can still contribute valuable data, especially when their orbits place them in positions unreachable by Earth-based observers. The presence of an interstellar comet in images from Mars rovers, in frames from orbiters, and in sensor logs from distant planetary missions underscores the interconnectedness of current exploration. Worlds are watching worlds pass, each with its own cluster of instruments and teams interpreting the faint signals. In this network, 3I Atlas acts as a test case in how to observe a truly fast transient event that moves not just through a field of view, but through the entire architecture of the solar system. The coherence of the picture that emerges, despite gaps imposed by viewing geometry and operational constraints, hints at what will be possible when a future interstellar visitor arrives at a time when interceptors are ready, and when this ad hoc campaign can be supplemented with a close, targeted encounter. Until then, the mosaic assembled from Mars, Earth, Jupiter, and beyond remains the most complete portrait of an interstellar comet in motion, a composite built from many angles that together show how a small, ancient body interacts with a mature system of planets and machines during a brief, shared interval in an otherwise immeasurable journey. As data continue to accumulate and analyses grow more detailed, 3I Atlas becomes not only a scientific object, but also a focal point for speculation about artificial origin. The idea that some interstellar visitors could be artifacts, probes, or debris from technological civilizations elsewhere in the galaxy has existed in the background of astronomy for decades. Each new object arriving from outside the solar system naturally invites the question of whether any of its properties demand such an extraordinary explanation. In the case of 3I Atlas, a handful of features seem, to some, especially suggestive. It is large for an interstellar body, likely several kilometers across, far bigger than the first known visitor and considerably larger than the second. Its speed relative to the Sun is high, higher than that of the previous interstellar objects, making it the fastest natural body of its kind yet seen. Its orbit is nearly coplanar with the ecliptic, passing close by several planets and the Sun in a sequence that, when mapped out, looks almost like a purposeful tour of the inner system. Its composition, dominated by carbon dioxide with unusual metal signatures, has no exact twin among known comets. To some, this combination of size, speed, orbital alignment, and exotic chemistry resembles a set of anomalies that merit a more radical hypothesis. A prominent theoretical physicist argues in a peer-reviewed paper and in less formal writings that 3I Atlas might be an engineered craft or device, or at least that the probability of such an explanation is non-negligible. In that framing, the high speed is not a coincidence, but a sign of deliberate acceleration. The near alignment with the planetary plane in the sequence of moderately close flybys become potential evidence of purposeful navigation rather than chance. The unusual composition and metal behavior are seen as hints that materials or coatings not normally produced in natural settings might be present. This line of reasoning catalogues several distinct features and labels them as anomalies, suggesting that while some may eventually be understood in conventional terms, others may remain stubbornly unexplained. From this mixture of suggestive but incomplete clues, an estimated probability of artificial origin is proposed, somewhere between roughly 1/3 and almost 1/2, a figure that is more provocative than precise. Within the broader scientific community, however, the reaction remains cautious and largely unconvinced. Astronomers, planetary scientists, and dynamicists emphasize that extraordinary claims require correspondingly strong evidence, and that in the absence of such evidence, the simplest explanations based on known physics and natural processes should be preferred. They note that the high speed of 3I Atlas is entirely consistent with expectations for objects ejected from other planetary systems in the thick disk of the galaxy. The velocity matches the spread of stellar motions in that population and does not require any special propulsion. The near alignment with the ecliptic can be understood through a mixture of observational bias and gravitational focusing. Surveys that are most sensitive to moving objects tend to scan near the planetary plane, where most known small bodies reside, so interstellar objects arriving on very different inclinations may be under-detected. The Sun's gravity also slightly enhances the likelihood that objects approaching from certain directions will be bent into paths that intersect the inner system. Statistical arguments suggest that if enough interstellar comets pass through the solar system, some will naturally have orbits that skim the ecliptic and pass near planets, without any guiding intelligence involved. To clarify what would count as compelling evidence for artificial origin, some researchers propose a set of observational criteria. One is an anomalous trajectory that cannot be explained by known forces. For a comet, this would mean accelerations that cannot be accounted for by outgassing or radiation pressure. The first interstellar visitor displayed a small, non-gravitational acceleration that sparked extensive debate, though models involving uneven outgassing and unusual shapes can, in principle, reproduce it. In the case of 3I Atlas, careful tracking of its path through the solar system reveals no such unexplained forces. Any deviations from purely gravitational motion are consistent with mass loss from the coma and tail, at levels expected from measured gas production rates. Another criterion is an anomalous spectrum or color. If an object's reflected light or emitted radiation showed features inconsistent with known minerals, ices, or gases, and instead resembled engineered materials such as polished metal alloys, composites, or other manufactured substances, that would be strong evidence. 3I Atlas, while unusual in its high carbon dioxide content and nickel behavior, still exhibits spectra that can be modeled with combinations of natural ices, dust, and organics, especially when its thick disk origin and metal-poor environment are considered. There are no sharp emission lines or broadband reflectance curves that demand exotic materials beyond the range of natural chemistry. A third criterion involves shape. An engineered craft might display geometries optimized for specific functions, such as flat panels, sharp edges, or regular angular forms, rather than the irregular, erosion-sculpted silhouettes of comets and asteroids. In principle, high-resolution imaging could reveal such shapes if a spacecraft flew close enough. At the distances that telescopes can obtain for 3I Atlas, the nucleus is unresolved. Its light curve suggests a roughly rounded or modestly elongated body, consistent with a rubble pile or compact cometary core, not a thin plate or symmetric polyhedron. There are no sharp transitions in brightness that would indicate flat faces or specular reflections. A fourth criterion concerns active signals. An artificial object might transmit in radio, optical, or other bands, either intentionally or incidentally, as onboard systems operate. Sensitive radio telescopes have monitored previous interstellar visitors for narrowband transmissions without success. Similar observations are made for 3I Atlas, scanning across frequencies where artificial signals would be most conspicuous against natural backgrounds. No persistent or structured emissions are detected beyond the expected noise and natural sources. The comet remains radio quiet, its presence betrayed only by reflected sunlight and the thermal and molecular emission of its coma. Put together, these criteria mark out a region of observational space where an artificial origin would stand out sharply. Unexplained accelerations, unnatural spectra, geometric shapes incompatible with rubble piles, and non-natural signals. 3I Atlas satisfies none of these. Every measured property, while sometimes at the edge of known distributions, still lies within ranges that can be modeled by combinations of familiar processes and plausible environmental differences. The high speed, the coplanar orbit segment, the carbon dioxide-rich coma, and the nickel lines without iron can all be framed as particular outcomes of formation in a metal-poor disk, ejection by giant planet dynamics, and long interstellar exposure. None strictly requires engineering. Yet the absence of decisive artificial signatures does not, by itself, prove that no technological influence is present. It simply means that there's no positive evidence. From a scientific standpoint, this is enough to keep 3I Atlas firmly in the category of natural objects. From a speculative standpoint, the door remains ajar in principle, though there is little reason to expect that this comet, among the many likely interstellar visitors, should be a craft rather than a fragment of rock and ice. The interplay between these perspectives reflects a deeper tension between curiosity and caution. On one side lies the desire to consider daring possibilities, to treat every rare and distant object as a candidate for messages or machinery from other minds. On the other side lies the discipline of evidence, the systematic insistence that hypotheses be tested against data and discarded if they add complexity without explanatory gain. In practice, astronomers continue to collect and interpret data on 3I Atlas with the same tools they would apply to any unusual comet. They track its position, model its outgassing, analyze its spectra, and compare it with populations of known bodies. They also remain open to the detection of anomalies that might arise in future observations, knowing that science progresses in part by recognizing when something truly does not fit. Beyond the immediate debate, 3I Atlas influences how future interstellar visitors will be approached. Missions like Comet Interceptor, designed to wait in space for a suitable target, are being planned with both natural and speculative possibilities in mind. If an incoming object is detected early enough and shows features that meet some of the more stringent criteria for artificial origin, a rapid intercept might be considered. Carrying instruments capable of high-resolution imaging, in-situ composition analysis, and perhaps even dedicated radio and optical monitoring suited to search for signals. Even if all known interstellar bodies remain stubbornly natural, these missions will offer unprecedented close looks at material from other planetary systems. There are also proposals for long-lived observatories stationed in deep space, tasked with watching for faint moving objects beyond the reach of current surveys and with following them over larger fractions of their orbits. Such platforms could extend the temporal and spatial baselines over which interstellar comets are studied, building a statistical sample large enough to test ideas about their origins and compositions. Within that future landscape, the story of 3I Atlas will likely be remembered as an early chapter, one of the first detailed multi-instrument, multi-vantage investigations of an object known to have formed around another star. It showcases the power of combining dynamical tracing, spectroscopy, and distributed spacecraft observations to build a coherent picture of a single visitor. And it illustrates how scientific and speculative narratives can intertwine without losing clarity. In the end, 3I Atlas remains, by all available measures, a natural comet, albeit one with unusual properties that illuminate unfamiliar regions of planetary formation space. Its path through the solar system has been fast and unrepeatable. Its materials are being released into space in a brief episode of activity after a vastly longer period of cold travel. And its presence has prompted humans to refine not only their measurement techniques, but their frameworks for considering what counts as evidence of something made rather than born. The mystery that lingers is not whether this particular object is an artifact, but how many different kinds of interstellar debris the galaxy holds, and how often such debris will intersect the sphere of awareness of technological species. Each new visitor will add data and nuance. Some may prove less exotic than 3I Atlas, others more so. Taken together, they will map out the diversity of building blocks and histories in planetary systems across the Milky Way. Until those future arrivals are found, 3I Atlas stands as a reminder that even without clear signs of technology, an ancient fragment of ice, dust, and metal, moving under gravity alone, can still serve as a profound messenger from another sun, carrying questions that reach far beyond the brief span of its visible tail.